All right, hopefully this one worked. Okay. 0.001332. So let's take a look at that here. 0.00132 versus 0.00, this is 0.001341. So we have 1332 versus 1341. This is going to be more accurate because we didn't make the simplifying assumption. And so we can see that, you know, when the percentage starts climbing higher, we're going to deviate. Versus if we did the quadratic on the previous one, we wouldn't have gotten a different answer. We would have gotten the same answer. And so since I did this using the essay, I'm just going to continue with the essay. This is going to be a side calculation here. But I already did this calculation, so I don't want to redo it. And so this is going to be 0.001341 molar and 0.001341 molar. All right. So should I worry about KW? You know, because the next biggest hydronium ion producer will be water. Should I worry about it? No, because water, the most it's going to contribute is 10 to the minus 7. And likely because of the common ion effect, it's going to be a lot lower than 10 to the minus 7. And so when we look at it, you know, this is 1, 2, 3, 4, 5, 6, 7. It might contribute here, but likely it's going to 10 to the minus 8, 10 to the minus 9, 10 to the minus 10. It's going to be out here. So that's not going to change this at all. And we're only allowed 2 sig figs, so it's not even worth it. And so the pH here is just going to equal the native log of this hydronium, 0.001341. 2.872. So I'm allowed I have 2 sig figs here, so I'm going to go 2.87, and then I'll carry one extra 2. So this is 2 sig figs here. Everything after the decimal is significant, everything preceding the decimal is not. So 2 sig figs. And so I'm going to start my titration at 2.87. That's the pH here. All right, where does the equivalence point come in? Well, the equivalence point comes in, we'll have to do a little calculation here. The nice thing about these numbers are the same concentration. So I have 0.100 molar acid and 0.100 molar base. Therefore, if I have 25 milliliters of 0.100 molar acid, how many milliliters of 0.100 molar base do I need to equal that? 25. So 25 milliliters will be the equivalence point. So like before, I'm going to calculate the half equivalence point, 12.5 milliliters. And so let's go ahead and do that here. At the half equivalence point, we are going to add 12.5 milliliters of sodium hydroxide. And so this is going to give us 37.5 milliliters of total solution. And then the acetic acid is going to have the same dilution factor as before. This is going to be 25 over 37.5 of 0.100 molar, which is going to give us what was it before? 666 molar. And then the sodium hydroxide is going to be half that because I'm only neutralizing half of the total. And so this is going to give us 0.03333 molar, 3333 molar versus 6666 molar. And then we pick the strongest acid, HAC, plus the strongest base. In this case, the strongest base is going to be sodium hydroxide. In the previous example, we didn't have any sodium hydroxide, so water was the strongest. And this is going to form sodium acetate and water. Now the situation about sodium acetate is not a neutral salt. And so if we go to the equivalence point on this titration, the equivalence point is not going to come at pH 7. In fact, the equivalence point comes at pH higher than 7, because what we end up forming is a salt solution, in other words, salt and water. And acetate is a base. And since it's a base, its pH is going to be higher than 7. And so the pH at the equivalence point is greater than 7. Well, anyway, getting back to this, we're going to have 0.6666 molar acetic acid, 0.03333 molar sodium hydroxide, and 0 molar here. K is very large, and so we expect very, very large, so we expect reaction here. K is very, very large. We have a strong base, but a weak acid. And so we're going to lose 3333, lose 0.03333, and we're going to gain 0.03333. And so that's not 0. This is going to be half. This is the half equivalence point, so we've only neutralized half of it, so half of it remains. So this is 0.03333 that remains. All the sodium hydroxide is gone. That's the only way we could neutralize half of it, and then we have 0.03333 molar sodium acetate left over. Now, this is our step 1 here. This was our step I. What kind of solution do we have? What does the product mixture consist of? Product mixture consists of, acetic acid and sodium acetate. And what you notice about acetic acid and sodium acetate is that they are conjugates of each other. And so we have a acid, acetic acid, and a base, sodium acetate, because acetate's a base. We have an acid-base pair that are conjugates of one another, and they're both weak. And so what type of mixture is this? This is an HH buffer. Now with an HH buffer, we're lucky because in step 2 is going to be the HH buffer. We're lucky because we could skip the ice table. We don't have to do it. We just use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation just says that the pH is equal to pKa. Well, the acid in this case is acetic acid, plus the log of the base is acetate concentration over the acid concentration like that. Okay, these are the initial amounts. The initial amounts are from step 1. So step 1, we end it with this mixture, and that's the beginning of step 2, but we're not going to go through the ice table. And so we're just going to go ahead and calculate the pH based on this being a buffer mixture. This is going to be the negative log. The Ka of acetic acid is 1.8 times 10 to the minus 5, plus the log of the acetate. The acetate is 0.03333. And the acid is 0.03333. And so that goes to 1. The log base 10 of 1 is 0. And then the negative log of that is 4.744 plus the log of 1, which is 0. And so the pH is equal to the pKa at the half equivalence point for a weak acid, strong base, weak acid, strong base titration. In fact, this is common knowledge. And so on a test, you wouldn't have to show the work. You could just say the pH is equal to pKa, that is, and you would be good. There are some other points that we get. This region here is called the buffer region. And in the buffer region, the pH stays kind of flat. And so it goes up a little bit and stays kind of flat. And then as we get closer to the equivalence point, it'll shoot up here through the equivalence point into the excess base region here. And so this, oh shoot, I'm having my pen. I'm not sure. Pens have disappeared. So this region here is called the Henderson-Hasselbalch region. And the reason Henderson-Hasselbalch buffer region, it's called the Henderson-Hasselbalch buffer region, or just the buffer region, because that's what we form. You know, after step 1, we're left over with a buffer. So the pH here at the center of this is going to be 4.74. Unfortunately, we're out of time, so we're going to do some more calculations in the buffer region next time. In fact, what we're going to do is, this is the half equivalence point. And so what we're going to do is we're going to do the 1/4 equivalence point and the 3/4 equivalence point next time. But that'll have to wait until after the weekend. This is still Chapter 17 stuff. The Chapter 16 stuff we're going to have the test on. And I was thinking of having the test in the lab on Wednesday in the lab. So the last part of lab I'll block off for the Chapter 16 exam. Is that okay?
Next week?
Next week, yeah. Okay. Next week is Chapter 16. Chapter 16 homework is a little bit long, so take a look at that, you know, early, so you can see it. I have your test back from 15.